13. This is colloids. So colloids are a different form of solutions in terms of solutions are homogeneous mixtures. Colloids are not. Basically what it boils down to is colloids are particles that will settle with time. The particles are large enough that they'll clump together and they'll settle with time. Whereas solutions, if you leave Kool-Aid out on the counter, it shouldn't ever settle with time. But if you leave milk out on the counter or just raise the temperature, if you heat up Kool-Aid, it really shouldn't change either. But if you heat up milk, it definitely changes because solutions are down to discrete particles, whereas colloids have very large particle sizes. There's 1 to 1,000 nanometers. Okay, yeah, nanometers are teeny tiny, but with respect to molecules or ions, they're huge. So in a solution, we call the solute, the particle that dissolves, we call that the dispersed phase. In solutions, it's a solvent, and in colloids, it's either a continuous phase or a dispersing medium, either one. Solutions don't settle with time, colloids settle with time. Now, some biologists, depending upon which subject you're in, they may take it as a solution if it takes 24 or 48 hours to settle. Again, in chemistry, that's a colloid. In biology, that may be a solution. So just be careful of who you're talking to as to how rigid their definition is. Now, the other huge thing is that solutions have no Tyndall effect, whereas colloids do. And this is the easiest way to differentiate between a colloid and a solution if it's clear. And what the Tyndall effect is particles are large enough to scatter the light. So what you'll see light particles, and this is really cool, and we'll get to that in just a second, but different colloids. One of my personal favorite colloids is marshmallows. Okay, butter, ruby glass, fog, smoke is one. An emulsion is a liquid colloid with an emulsifying agent. Now, that's cheating because you're not supposed to find a word with the same word. So an emulsifying agent is something that's soluble in both polar and nonpolar. So these are the things that allow like oil and water or oil and vinegar to mix. If you look at this, mayonnaise is a common one. It is, let me put it over here, it's an emulsification. If you're making it from scratch, you use egg yolk. And egg yolk has a particular enzyme in it that allows the oil and the vinegar to come together. And that's really what mayonnaise really is oil and vinegar combined with a little bit of seasoning and spices. Okay? So that's what an emulsion is. Now, we talked about the Tyndall effect, and this is one of my favorite, is what it really is you can see the light beam. So what we've got is, this is a colloid, like you can see that because it's red on red. This is a colloid, and this is a solution. Now notice you cannot see the light beam. Here you can see the light beam in this area right here. And you may not be able to see the entire light beam, but it'll appear milky or cloudy. And that means that the particles are large enough to scatter the light. And remember, the Tyndall effect is when the light is scattered by particles. And they're scattered due to the size. And again, we're talking Still teensy, but we're talking about large particles as compared to um, light beams. Okay? So it's kind of like, are you tall or are you short? Well, if you're standing next to Shaquille O'Neal, I can guarantee that you're tall. You're short. Sorry. Well, at least I'm really short. And if I'm standing next to a 2-year-old, then I'm tall. Okay. Shaquille O'Neal is gigantic. But so it's all relative. So in the case of the Tyndall effect, the colloid particles are large enough to scatter the light. Now, this is a cool slide I got from the previous Pearson text, and you've seen this, and you'll see this if you're looking at clouds and you see the light beam coming down. They call that God light. Well, all this is dust in this library area, hallway, whatever, and you're seeing the dust scatter the beams of light. So this is the Tyndall effect. So you can see it there. Now, how do colloids stay suspended? Okay, the particles are neutral, but as they go around, they surround themselves with a layer of electrons. Now, once you get electrons on each other, they're going to repel. So if you'll notice that you have the electrons and they're going to repel. So these little particles keep bouncing off each other and they stay in motion. So if you look at it, Brownian motion is the term that keeps the particles in suspension in a colloid suspended. Okay, and basically what it is like bumper pull or bumper cars. So what happens is this particle goes and hits another particle and then bounces over here, and they keep hitting each other, and so they keep each other moving. So if you've ever taken a balloon and it was not full of helium but full of air, and you put a whole bunch of them up and you have people running around pushing them, okay, and you keep them from hitting the floor. It's a game. If you're kids, you can do this, okay, and the distance traveled in between collisions is called the mean free path. And so what happens is as long as they have enough energy to keep knocking each other, then they don't tend to knock together, nor they tend to fall out of solution. So Brownian motion works much better for particles that are smaller than for larger. Now, this is from a Brooks Cole text, and this actually shows Brownian motion in a liquid. Now, most of y'all are probably not of age, and even if you were, this is a dark beer, like a stout, which I find totally nasty. But a bunch of guys in England were sitting there drinking, and what they were noticed is they were able to see the bubbles. And in the stout beers, they have enough sugars, etc. They're a very thick beer. And what actually ends up happening is the bubbles go up and then they'll impact something else and go down and around. And you're like, bubbles aren't supposed to go down. So in champagne, the bubbles just go straight up. It's because it's a very light, not very viscous liquid, whereas stout is. So if you have a viscous liquid, then you tend to have the bubbles revolve. But you don't if there's nothing to stop them or slow them down, because the sugars and the proteins are making them bounce off. So that brings us to the question of, how do you get rid of a colloid? Okay, well, we call getting rid of a colloid coagulation, because basically what you're going to do is allow them to come together, and when they come together they form a much larger particle which is much heavier, which will fall out of solution. Now, there are 3 ways to do it. The first one is the application of heat. The second is the neutralization or the addition of ions. And the third one is the electric current. Well, we're going to start with the second one because I have this pretty picture. And what you're doing is you're adding ions to the colloid. Well, an add effect of that is, remember the colloids surrounded themselves with negative particles, remember? Well, once they've surrounded themselves with negative particles, they repel. Well, what happens then if you put some positives on those negatives, make it neutral, and then they start colliding and they'll stick together instead of repelling. And then once they form a large clump, if you'll notice down here, this is where the particles get large and they settle out. And aluminum sulfate is commonly used in water treatment plants to get particles to settle out of water. Okay, that was the first one. The second one. Let's go back to heat. Well, think about it. If you increase the temperature, you're going to increase the kinetic energy. You're going to increase the collisions of the particles. Well, think about it. If two bumper cars collide, they're the same weight. They're going to bump off each other. But what happens if somebody snuck in a small tractor? Small tractor is just going to roll right over the bumper car, because if they have enough energy to collide, they will overcome the repulsion and form bigger particles, which again coagulate and drop out. Bigger particles which get too heavy to stay in suspension and they drop out. See a theme here? There's you're trying to get things to group together so they're too heavy and they fall over. Okay, the last one is electric current. Okay, well, if you have an electric current, you're going to have a negative side and you're going to have a positive side, right? So as these particles come through, if they're coated with negative electrons, they're going to stick to the positive side. Now, if you've ever had an air filter that is the kind where you shut it off, unplug it, and then you pull the filter out and it's the metal plate and it's all black and you just wipe that off. And they make it sound like this is fabulous, and it actually is a pretty good idea. But basically what you're doing is you're applying a current across the plates and you're picking up the particles, and so instead of them coming through, they're attracted to that side. If they happen to have picked up a positive charge because they've got ions in them like sodium or whatever, then they'll be picked up on the negative plate. But the net effect is you used a giant magnet to pull them out of solution. And again, the object of the exercise with colloids in coagulation is to get them out of solution. Now, this occurs in nature. This is a river delta. And what's going on here? Well, as the freshwater river comes downstream, it's picking up silt. Notice you can see all of the dirt that is picked up along the way falling out. This is why river deltas build up. You know, the Nile River, they let it flood, etc. And it's because, guess what? This is salt water. I think this is New Orleans, so that's the Gulf of Mexico. And so it has ions in it. So the net effect is you got this fresh water and is carrying these particles, which are neutral because they've picked up electrons. And then it hits all the salt water, and all of a sudden it's like, whoa, the charges are neutralized. I'm going to coagulate and dump out. This is actually how surfactants work. And remember, the rule is like dissolves like. If that's somebody asks you, that's what you ought to remember. And hydro is water, and philic is loving. Okay, so a bibliophile is somebody who likes to read. So if it's hydrophilic, it's water loving. So that means it's polar. If it's hydrophobic, if you have a phobia like agoraphobia, you're afraid of heights, arachnophobia, you don't like spiders. So you're water hating. So you tend to be nonpolar. So if you take and combine these into a fatty acid salt. Oh, I have that written there. Then this portion are all CH2 groups, CH2, 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 which this area is called the tail group. And it's all nonpolar because it only contains carbons and hydrogens. So it's nonpolar, so that means it's hydrophobic. On the other hand, at the other end, you have your carbon with a double bond oxygen and an OH. That's your fatty acid part. Okay, this is going to be what they call the head group. And because of the OH, all the O's in it, and if you take off the proton and replace it with a sodium ion, then you got a positive and a negative. It is definitely polar, so it's hydrophilic. Now, this is soap. Okay, and saponification is a fancy term for making soap by taking lye, which is potash, a base, and combining it with lard, oil or fats, to form these fatty acid salts so that they will dissolve oils. Now, how do they work? Well, soaps work by forming something called micelles. Not your cells, micelles. No, ha ha ha. And these micelles form by surrounding little droplets of fat. Droplets of fat. And surrounding them isn't exactly the right word, is they form these little oil droplets. And they're formed by fat with the fatty acids. And what happens is the oil droplet, so we get the, we call this the organic phase. That's a fancy name for nonpolar. And this is the water phase, which is a fancy name for polar. Okay, so what happens is you get these little bitty droplets that have the fatty acid salts with the nonpolar end holding little droplets and the head group sticking out so they'll dissolve in water. And this is actually cool. You can do this at home. So if you take a little couple drops of oil in water, it sits on top. Big fat deal. So if you add soap, Dawn, whatever hand detergent, and stir it up, then your oil on top will disappear. But your solution goes from clear to cloudy because you have created a colloid. So the other fun thing to do is shut off the light, get the flashlight before you shut off the light, and then shine the light through it. And what you'll do is you'll see the Tyndall effect once you've formed this colloid. Because what these little bitty micelles are what is dissolving the fat and moving it throughout. Okay, so this is actually a cool little experiment you can do at home, and I highly recommend it, is to play with soap. Okay, has its fun properties. Okay, the next one is chemistry and life. This is sickle cell anemia, and this has to do with the proteins, etc., that are in the red blood cells in people. And sickle cell anemia, they can deal with it now, but it actually is a preventative. If you have the sickle, your red blood cells, sickle's not red blood cells, then it's actually you don't get malaria. So sickle cell is kind of interesting because it's one of those things where it's a disease that actually has a purpose. And it's kind of interesting to read, especially in this day and age of the COVID. everybody thinks that everything is all bad or all good, but there are actually some cases in the COVID-19 we're still out on, other than it has pretty much disrupted our lives, and we're having fun online because of it. But the bottom line is that in the end, we might actually find something that comes out of it positive. At this point in time, not so much, but you never know. But read over this, because this is actually really important, and it applies to your life. We are done with chapter 13. The first test will be 11, 12, and 13. 12 is posted, and it is strictly a handout driven, and you'll get bonus points on your test for doing it. How many bonus points is a function of what basically I need to give you. I mean, if the test average on the first test is high, then you might get, 5 or 6 points. If it's low, then you may get 10 or 12 points. It truly is a function of what I need it to be. And that will be posted with a simple explanation. I'll probably try to make a little video of that shortly as well. Okay, so we're done with chapter 13, and we'll have the test and move on to 14.